Hello everyone, welcome to this taster lecture. My name's Nick Hawes. We're going to talk today about an area that's close to my heart, which is probabilistic robotics. As you can see from the video there, well, in fact, these videos are kind of instances of research. So I'm from the Oxford Robotics Institute, which is a part of engineering science. It's across the road. And there we do all sorts of robotics work that is, well, spans from kind of building robots to programming robots and everything in between, and I'll talk about a little bit about that in a minute. Just to let you know, I mean, as many of the people that you'll meet today, I wear two hats. One of the hats is an associate professor hat, so I work in the engineering science department. I lecture students in the second year on programming and computer architecture modules, and also in the third year on C++ and software engineering modules. But I'm also an engineering fellow, so I do my tutorials down at Pembroke College. And as a very quick plug, if you haven't decided to go and see Pembroke, please do come down. We're a little way down. We're opposite Christchurch, down sort of the other side of the city centre. It's a lovely, very friendly, modern, progressive place. Medium-sized in many dimensions, and a great place to come and see. I'll be there from 2 o'clock till about 3:30 this afternoon if you want to talk more about robotics or artificial intelligence, or experience a little bit more about Pembroke down there. So do come down and say hi. So I mentioned that I'm from the Oxford Robotics Institute. There we do all sorts of robotics, from flying systems, wheeled systems, legged systems, on-road, off-road, in buildings, around buildings, all sorts of things. What we do is almost anything that takes lumps of metal and plastic and makes them intelligent and autonomous, allowing them to work for humans in all sorts of situations. Typically, we want to automate robots. We want to make them autonomous so they can operate in situations that are dull, dirty, or dangerous, because humans don't want to be there. Now, I'm showing you this because they all have something in common. When we look at robots and we think about creating novel robotic capability or novel robot software systems, these things have lots of things in common. One of the key things for today is that they all involve maths, they all involve programming or software in various forms, and they all involve thinking about a broader system. So a collection of interacting devices, whether that's hardware or software. We can think about these things as a system. So this is kind of fundamental to modern engineering. Ultimately, as engineers, we think about the world in the language of maths. Right? We write down how these things are going to behave in logic and maths, whether that's kind of the mechanics in physics, whether that's what we'll talk about today, probability theory for the behavior. But ultimately, we formalize the behavior of robot systems using maths. We make that maths work for us by programming. Okay, that's how we implement those mathematical ideas. And then ultimately, we build and evaluate these systems in the real world by thinking about them as systems and the way they interact with the broader sense. So all of this is kind of core to engineering science. And I'm going to illustrate all of this with a particular example. So the problem is another thing that all those robots have in common, which is the question of how does it know where it is? Now, this is a slightly weird question. So as humans, you're all sitting in the audience going, well, why is that difficult? I know where I am. Hopefully, you all know where you are. You traveled here this morning. You sit in a lecture theatre. You look around you. You know kind of where you're located. And you're doing that by reference to all sorts of things, right? As you've walked in here, you've remembered the spatial layout. You can look around and kind of see where you are in space. And that's kind of easy for humans, but it's actually very, very difficult for robots. But it's really important for a robot to know where it is. If you're building an autonomous delivery truck, that robot has to know where it starts, where it ends up, and how to choose which route to take between, the start and the finish. If you're building a robot that's going to get you a drink from the fridge, the robot needs to know where the fridge is and where you are. So knowing where you are in space is key to almost every part of robotics. And it turns out to be quite a difficult problem. The problem we're going to talk about in particular is probabilistic localization. So I'll break that down into two parts. The first part is the kind of localization part. So localization is the process that works out where a robot is located. So we care about the location of the robot. And in general, this process is going to use the robot's sensors to compare its current location to some kind of map. So when we think about where the robot's located, we're going to do it with reference to a map. So the map is going to be the thing that tells us allows us to work out kind of a coordinate frame for the robot, for example, or a location for the robot. And we're going to use the robot's sensors to look at their surroundings and kind of use that to determine the position on the map. And what's going to be key to this, and I'll justify this a little bit more as we go on, is taking into account uncertainty. Uncertainty occurs almost everywhere in robotics. So uncertainty implies that we don't know what is going to happen, or we don't know everything with full certainty when we look at the world. So there's many reasons why this happens in robotics. If we're talking about location, even if the robot, for example, knows exactly where it's located right now, and then moves in one direction, we already get uncertainty there. So when a robot moves, a wheeled robot, for example, counts the number of times its wheels turn to work out the distance it's moved in one direction. But if the wheels are on a slippery surface, maybe the robot goes through a puddle or goes through some thick carpet, that's very hard to say, what happens is the wheels will turn with the same amount of force. The wheels may turn with a different amount because of the different frictions it's experiencing, and that makes the counting inaccurate. The other thing a robot might do is use a sensor to measure how far it is away from a wall, for example. If you've used a laser tape measure, that's the kind of thing a robot might use to measure how far it is away from each wall. But as the wall gets further away, that reading you get back from the laser gets less and less accurate. So I can be super accurate at short distances, but at long distances, I start to get uncertainty or noise in my laser readings. So even working out my relative position can start to be uncertain. And there's also problems that even if I'm, for example, measuring my distance to this desk, and this desk might be in my map, and I might say, okay, I know I'm sort of 30 centimeters from this desk. Maybe Tom, who did the previous lecture, came in and moved the desk slightly. So maybe my relative position to the desk is correct, but my global position is uncertain because someone's moved the landmarks. So all these things will affect the kind of accuracy of the localization. And if we can measure them and model them mathematically, then we're going to be able to take that uncertainty into account when we try and work out the location that our robot is at. So I'm going to work through this in kind of a sort of a progression of increasing detail. So this is the way I like to teach. We do this when we're teaching computer architecture or algorithms. I'm going to start with a kind of conceptual overview. I'm going to give you sort of a visual idea about how the algorithm and the process is going to work. And then we're going to drill down a little bit into the mathematics of how you actually model and implement this on a real system. And that will give you kind of the sort of the key engineering understanding of this. So I mentioned earlier we need a map. So we start with a map. And that map's going to have landmarks. So I kind of hinted at this a little bit to start with. The robot needs to be able to know where it is in the map by using its sensors to measure its position relative to some landmarks. So we might start off with a kind of human-friendly map that contains all the things that we might use as landmarks in a home. And then we're going to say our robot is going to need to work out where it is in that space. So, for example, I could draw a picture of a robot. So this is the robot. If you saw on the very opening slide, you saw a yellow robot driving around. We've got yellow and blue versions of those robots, Bob and Betty. This blue one here is Betty. And it's kind of interesting. I can draw the picture of Betty on the map, but that's us looking at Betty, knowing Betty's position. You have to imagine that you're in Betty's head trying to work out where you are, and all you're only able to do is take observations. So that's a sleight of hand. When I draw the robot on the map, you're going to have to imagine that we're an external observer so we can see what's going on. It's a bit different from the robot's perspective. So now the question is, how do we make localization work? How can we build an algorithm that helps the robot determine its location? And the answer is this. This is how we're going to do it. Can you stick your hand up if you know what this game is? Most of you. What's it called? Someone shout out. Guess Who? Excellent. You're a talkative bunch as well. Perfect. So it's weird. Sometimes I get no hands at all. There was some generation where Guess Who was taboo somehow. Anyway, Guess Who is the way we're going to do it. So if you don't know Guess Who, the way it works is you're trying to guess which person, there's someone opposite you, they've got a card which represents one of these faces, and you ask questions, and you can use those questions to determine who you've got. So you might say, has the person got glasses? And if they say yes, you flip down all of the people that don't have glasses, and you're just left with the glasses wearers. And that narrows down the space of possible faces you're trying to guess, okay? So the thing I want you to think about is the question asking process is what our robot is going to do with its sensors. So the sensor on the robot is going to be equivalent to asking a question. And then the flipping down process is what we're going to do in localization. So we're going to have algorithms that flip down the faces for us, and the faces that get left are the possible locations the robot can be in. So we're going to turn our map into a Guess Who game by dividing the world up into a grid, and every grid is going to have a robot in it. So each robot there is a possible location or a possible answer to the Guess Who question. And the next thing we're going to do is ask questions. So the question we might ask is, for example, using computer vision. So we've got a camera on the robot, and the robot might ask, what can I see? I'm in some kind of room, what can I see? And maybe if the robot sees a pot plant, then what we're going to do is we're going to remove all of the guesses in rooms that don't have a pot plant. So that's only one room there. And then we might do the same with books. And so we can remove all the guesses from a room that doesn't have books, and then maybe TV, and we get left with this guess. So the robot is observing things. So imagine you're Betty, you're stood there, you open your eyes, you turn on your camera, and then you see, okay, I can see pot plant, books, TV. And then I go to my map and I remove all the guesses that aren't in a room that has all those three elements. And that leaves us with a bunch of guesses in this room. Now, as you can see, that's still quite a coarse description of a location. The robot could be anywhere in that room because we've only been asking questions at the level of rooms. And that would turn out to be pretty useless for many robotic tasks. If you want to actually go and get a book from the stack of books or turn the TV on and off, you need to know more than what room you're in. You need to know a more precise location within that space. So instead of just thinking about the rooms, maybe we'll exploit some physics. Right? We know a camera is looking at reflected light. That can only travel in a straight line if there's no obstructions. So maybe we'll think about looking at each location and trying to work out whether the object in question is actually visible from that location. So we could draw a straight line from every robot and say, can I actually see a pot plant from where I'm stood? And so our Betty guess there can't see that pot plant because it's behind a stack of books. And so therefore we would remove that from our guess. And the same for here. And then we might do that all over the map. So any location that doesn't have a straight line between it and a pot plant, we would remove. So this is using kind of more detailed information. So our guesses are getting kind of more fine-grained. And we could do the same with books, and that will remove more, and TVs, and that will remove more still. And so now we're really starting to narrow down that location. And you can see that the answer now is slightly more fine-grained. We know a little bit more about where our robot is. And you can think about this. If we're thinking about this as a probability, you could imagine that now the location of the robot is described by some probability distribution over every cell in this location. And now we've only got probability mass, so numbers greater than 0, left in the cells where we see a guess. So that's going to be where we're going to get to with the probability here. So I kind of promised a bit of maths, and we'll get to there in a minute. So we've shown that we can narrow down our robot's location by taking into account our sensor and some information about that sensor, that it can only go basically in a straight line. But what I've shown you isn't really what happens on robots, because computer vision on robots is really hard. So if you've got a robot driving around in an unstructured world, it becomes very, very difficult for that robot to observe the world reliably. So this is an example of a computer vision result that we ran from an object classifier. So it looks for types of objects. We ran this on a robot a couple of years back. It was actually using a 3D shape-based recognizer. So it was using 3D images to try and detect classes of objects. That's why the back of the chair looks like a bottle. Okay? It says this is a bottle, because actually you can imagine that's a wine bottle lying down or something up there. And this person is a mug. Which, you know, I'm not make any comment on that. I like to think it's because his arm's out like that, and maybe he looks like a handle of a mug, but I think I'm maybe reading a little too much into it. But this is quite a bad result. I picked this because it's an extreme. But it does show you the difficulty of actually doing this kind of object recognition online with robots. So instead what we're going to do is distance. So most robots you'll see will have some kind of range sensor on them. That might be laser, sonar, radar, things like that. And you'll have a laser scanner that can quite accurately measure distance within a certain range. And for example, on Betty, we have a laser scanner that gives us a 270-degree range around the robot, up to about 30 meters, at quite fine resolution. So we can measure the distance between the robot and the obstacles around it. And when we use that laser scanner, we need to turn our map, or we need to move our map away from types of objects, where we might label them as pot plants and books. And instead, we'll just care about free or occupied space. We only care about the things our sensors can detect. So if all our sensor can do is measure the distance to some kind of obstacle, something that reflects the laser, then all our map should contain is things that will reflect the laser or not. We no longer care whether it's a pot plant or a toilet. We just care that it reflects the laser or not. But then the Guess Who game is largely the same. So we populate our space with guesses. And then the questions we're going to ask will be laser measurements or distance measurements. Now, I'm going to cheat a little bit and make this simpler so I don't have to do too many lines on my slide. And let's imagine, again, Betty up here has woken up, turned on her sensors, and she's just got one laser measurement, and that goes out to the right. And that measurement is currently reading 4. So we're going to assume integer-based laser measurements, which is, of course, incorrect. But we're going to get a reading of 4 back. And that 4 could correspond to 2 things. In this case, we're going to say either that means the laser passes through 4 empty cells, or we could say that the maximum range of the laser is 4, and therefore 4 empty cells could mean 5, 6, 7, or 8. That's actually an additional complication that we won't worry about in too much detail, but you have to model that if you're using a sensor. Again, you have to model the range and the ability of that sensor, for example. So we're going to see a reading of 4 from our laser scanner. And then what we're going to do is say which cells in the environment would possibly support that reading. Okay, so the laser tells me that the reading is 4. And so now I need to look at every guess individually and say, is it possible that that cell would also give me a reading of 4? Is that a kind of a viable hypothesis for my location? So this one it is. This one it's not. I would only get a reading of 3 from that cell, so I can remove it. Same here, I can remove that. That would give me a reading of 2. So because I've got a reading of 4, I'm not going to use that. And if I apply that to every location, I'm able to narrow down the space and ask again the question, where is the robot? And the answer here is, well, we still don't know. We still don't know. But what we're doing is we're forgetting something. So Betty here is a mobile robot. What feature of a mobile robot have we not used yet? Someone stick their hand up and tell me. What have we not used? Let's go middle at the back. Yep, you. Movement, exactly. Wheels, all of that stuff. So our robot can move. So let's imagine our robot can move 1 step downwards, 1 step forwards. And what we do is we interpret that movement by shifting all our guesses. And again, we can remove any guess that is impossible given the things we've observed in the world. So if we're able to physically move 1 step, we can see that there were some locations that weren't able to do that. If we then take another reading, for example, get a reading of 3 back, we're then able to really narrow down the possible locations of our robot. And this is largely how things happen in practice. We use distance-based measurements, we scatter guesses all over the map, and we refine those guesses through a loop of sensing and movement. Okay? This is the localization process. The big difference between the way we do it in practice on our robots and the way I've demonstrated here is we don't have a grid. We actually have kind of free floating guesses that we can kind of scatter over the world, and they kind of coalesce over time. But that's something I can talk about later if you're interested. Now, I did promise you some maths, and I know you all love maths. That's why you're here to be engineers. So I'm going to talk a little bit about how we can actually implement this in practice in a mathematical model. So what we're going to do is we're going to make an even simpler world, because this allows me to illustrate these things more clearly. And in our world, we have a robot, and we have 3 possible locations. So now we've only got 3 cells our robot can be in. It can either be in the top, middle, and bottom, and our job is to work out which location this is going to be in. So again, I promised probability. So if you're familiar with the idea of a random variable, we're now going to represent our location as a random variable. So the variable will be called location, or sometimes I'll shorten it to loc. And the values it can take are either C1, C2, or C3. And we're going to think about the probability distribution over those locations. So now we're going to turn this into a probabilistic inference problem. So let's assume that I know nothing about the robot's location. I have no prior knowledge, but I want to write down a probability that the robot is in one of these locations. What probability should I write down per cell? There was a hand quickly at the front. Yes? 1/3. 1/3, yes. So we have a uniform probability distribution over the location. We don't know where the robot is. We have total uncertainty. So we say, look, the probability of the robot being in any of these locations is evenly distributed across those places. And our job performing localization is to update these probabilities using our sensors. Now, what we're going to do is look at how we model the sensors. In the previous example with Guess Who, I didn't really talk about sensor uncertainty. But now we've got the mass there, we can start to think about it. So instead of having objects, what we're going to do is we're going to paint the floor of each cell or each room, and we're going to have pink and yellow rooms. And we're going to have a kind of another random variable that's going to refer to the value that our sensor gives us back. So our sensor might give us pink or yellow as a result. And then we're going to have a dodgy sensor. So if you've ever done color sensing on Lego robots, they're very dodgy. If you've ever done object sensing on robots, as you can see, the results are typically uncertain. And we're going to model this mathematically. So in this very simple case, we've got either pink or yellow. And when my robot is pointing its sensor at pink, the probability that our reading is pink is going to be 80%, and the probability that it's yellow is going to be 20%. So you can think about that as effectively 80% of the time my sensor gives me the right answer, 20% it's wrong. And we'll do the same for yellow. So 20% of the time it's wrong, 80% of the time it's right. So when I point it at yellow, I get the reading yellow back 80% of the time. So this is what we call a sensor model. And this is the mathematical, or the quantification of our knowledge of the way the sensor behaves in the real world. We're saying our sensor is imperfect, but we're able, as roboticists or engineers, to quantify that uncertainty and write it down. And then what we're going to do is we're going to build a relationship between the two random variables we've got. So we've got our location random variable, and we've got the color random variable that we sense. And we can build a graphical model, so a graph that says the location causes the color. Or maybe not even causes. The random variable here, color, is conditioned. It's a conditional probability given the location. And using that, we can write down a conditional probability table that says for a particular location, what's the probability that I'm going to observe a particular outcome from my sensor? Now, this is actually where the magic happens. What we're doing is we're saying this table captures the relationship between space, which is our map, and sensing, which is our sensor model. It tells us, depending on where our robot stood, what's the probability of getting different readings. And that's what we're going to use in our Guess Who model to kind of flip down the guesses. We're going to use this to actually work out our locations more accurately. So we're going to call this a sensor model because it's modeling the behavior of the sensors. And all we need to do now is work out what the mass is. So what we're going to do is we'll start with our prior distribution or prior probability, the thing we know before we do the maths. We're going to write down our probability table, and then we're going to use something called Bayes' rule. So Bayes' rule is absolutely fundamental in robotics, in particular in probabilistic robotics. And what it allows us to do is take conditional probabilities and prior probabilities on the right-hand side, which we know. So these are things that typically we find it easy to write down or measure. And Bayes' rule allows us to calculate the thing we don't know but we care about on the left. So we care about the probability distribution over our location given the color we've observed, but we can't write that down. What we can write down is the probability of getting a color given a location and our prior probabilities. So we can write down a version of this mass for each location, and then we can pull these numbers out of the table and out of the prior probability distribution that we've got. And then we can do some maths. What we're doing here, there's a normalization constant here, alpha. All that's going to do is make sure that this probability distribution sums to 1. There has to be, for a correct probability, it has to sum to 1 over the cells. And therefore, we can work out this unnormalized and then normalized distribution, given the observation we've made. So here we're assuming that we observe pink. And that should kind of have some intuitive sense. If our sensor is more often right than wrong, and it tells us that we're looking at a pink surface, then it's more likely that we're going to be in the top or the bottom. Okay? So this is how the mass works, and this is absolutely the mass we use in our localization processes. We can also think about movement, and we're just going to do this very quickly, that movement can also be thought about probabilistically. So the location at time step t, now we're going to think about time, is influenced by the location we were at previously. And the way we deal with this in practice is going to be reasonably simple. We take our initial distribution, we make an observation, so that says we're more likely in pink. And then again, we do exactly what we did. We sort of sweep our guesses around based on the movement. In this case, if we assume we move down, we're going to sweep our guesses down. And that really just has the effect of squishing our probabilities down to the bottom, okay? So we thought we were we had this distribution, we moved down, that squished our distribution down here. We're assuming we can't fall off the bottom of the world, so the probability mass accumulates at the bottom. and then say we get an observation of yellow, well, that now tells us we're more likely to be in this location. This model assumes that movement is 100% accurate. If movement was uncertain as well, you typically see that we leave some probability in the top. In this case, because I've said movement is deterministic, we just push all that probability. But if it's non-deterministic or it's uncertain, we would smear the probability. We'd leave a little bit of probability behind. Okay, so that's how the maths works at a high level. And really, what I've given you is really a very potted example of what engineering is. We had a problem. We wrote down the problem, we dealt with it conceptually, we thought about the system, and then we wrote down some maths that allowed us to think about it in a formal way, and we showed how that maths sort of matched our intuition. This very much is kind of engineering science in a nutshell for me. The robotics works I talked about is not something you do in your first 2 years. The first 2 years you cover very general engineering topics, but in the third and fourth year you can specialize in programming, probabilistic methods, things like localization and robotics. There are robotics projects and courses in both the third and fourth year, alongside things like machine learning and software engineering, which are all key to modern robotics. This is all part of what's called the information engineering specialism. It's a bit of it's a word you don't hear outside of many universities, but if you want to do AI and machine learning in engineering, we're part of the information engineering area. And as a student, you also get an opportunity to play with robots. I say play, it's hard work. Work with robots directly outside of these areas. This is our RoboCup team, so this is from a few years back. So half of these people here are undergraduate engineers. They're taking part in something called RoboCup. RoboCup is kind of an international competition for robotics. So they do both football robots, so soccer robots, and domestic robots, so robots that help in the house. There's actually a robot here. It's actually a very bad picture. You can see more people than robots, but this thing here is people are more important than robots, I should say that. There's a robot here, which is a robot with an arm that does domestic service tasks. These lovely people are off to Bangkok in a week to compete in the Domestic Standard Platform League. And this could absolutely be you. You could come here, start working on robots in this team from year 1, and then by year 3 or 4 be traveling the world to compete in robotics ideas, robotics competitions. So that is pretty much it for me. Thank you very much for listening.